Welcome, listeners. Today we have gathered here to start the first lecture in the series on the subject Fundamentals of Geology. My name is Dr. Shandy Banerjee, a faculty member in the Department of Geology, Banaras Hindu University, Varanasi. So, we'll be dealing to start with, we'll be dealing with the origin of the universe. But as we all know that universe, it's an infinite thing, and actually to deal with universe, we need an infinitely long series of lectures. But obviously, as we are looking into the fundamentals of geology, so here we'll try to see in a very you can say shortened form of what is all about universe we can learn, as well as we will try to look into the universe in the perspective of a geologist. So, to start with the origin of the universe, and obviously we need to know that why it is necessary to study about the origin of the universe, and also where we stand or where we are exactly existing within the broader framework of the universe. So, the history of the universe we will try to sum up in one easy lesson. So, we'll look at the beginning of the universe, then we'll see where we are, and we'll try to also think about that how everything might end at some point of time. So, to start with, before the beginning of the universe, every civilization has a creation theory that explains that how all has started. All of this begins with nothing at all, and this relates to a lot of creation stories. It all started with a singularity or a cosmic egg, a tiny seed that held all the matter, but keep in mind that there was nothing at all, no time, no space, no void at all. So, singularity means nothing, but singularity is a non-dimensional spot. Apart from that, we can also think in a manner that there was a primeval atom that was present at the singularity. Also, you can think of the expansion of that atom resulting from the process of the Big Bang as we know it. So, nothing became anything in an instant. So, one of the famous Belgian astronomer, Georges Lemaitre, he proposed the idea of singularity from what all began, and he also proposed the idea of the primeval atom or the cosmic egg that rapidly expanded, leading to the formation of the universe as we know it. And just from this simple figure, you can see that Google has also prepared a doodle for the contribution of Georges Lemaitre for the idea of this primeval atom or the presence of the singularity at the start of the formation of the universe. So, at the moment of the Big Bang, that is the beginning, the universe started to expand, cool, and become less dense. The universe is still expanding today. So, now if I look at the radius of the visible universe like this, and if this is the singularity from where the Big Bang took place, then it got inflated, having stages of quark soup, then big freeze out, parting company, formation of the first galaxies, and the present universe that we now see. So, the evolution of matter since the Big Bang can be quantified or can be classified under certain era. The first one is the Planck era, that represents the first 10 to the power minus 43 seconds just after the Big Bang. Then you have the quark era, that represents the 10 to the power minus 12 to 10 to the power minus 6 seconds after the Big Bang. Then comes the hadron era, that represents 1 micron of a second to 1 second just after the Big Bang. Then you have the lepton era, that represents 1 second to 10 seconds soon after the Big Bang. Then comes the radiation era, that proceeds from 10 seconds to 3 lakh years after the Big Bang. So, if I just try to visualize the universe, then it started obviously with the singularity, and it started to expand, and now the galaxies that have been formed after the process of the formation of stars and formation of galaxies, now they are also separating away from one another and it is expanding. So at the beginning, if I again start with the primeval atom, and obviously at this stage, or you can also think of singularity, that is a non-dimensional spot. So there is nothing but energy, there is no matter in it. But as Einstein taught us, like E is equal to mc square, so energy can be converted into matter in due course of time. Now coming into the subdivision of an atom that represents the presence of also energies, that are energy particles that are represented as quarks, and physicists have very beautiful names for it. There are 6 kinds of quarks: up, down, charm, strange, top and bottom. So if I now combine the ups and downs in a particular pattern, like if there are 2 quarks of up, that means plus 2/3 charge. If I combine 2 ups with plus 2/3 charge with a down with minus 1/3 charge, then you can generate a proton. Similarly, if I combine 2 downs with minus 1/3 charge and combine it with one plus 2/3 charge up, then what you get is a neutron. So the first atom that might have formed soon after the Big Bang was definitely an hydrogen atom, which has a proton and simply bundles of energy, that is electrons, surrounding it. And as it goes on along with the Big Bang, multiple hydrogen atoms started to form. And after the initiation of the formation of the hydrogen atoms, there have been phases where these hydrogen atoms, they combine to form little bundles of hydrogen atoms, and eventually they started to rotate within the universe, or simply just after, I'm talking about a time soon after the Big Bang. And as they started to rotate, what happened, that as Isaac Newton told us, that if your bundles of matters are rotating, then obviously there will be gravity that will get exerted onto one another during the rotation of that matter. So eventually all these hydrogen bundles of hydrogen atoms, they started to collide with one another and they started to release a lot of energy, and obviously that energy is nothing but heat. So it gone into you can say a large amount of heat, approximately a few million degrees centigrade. And eventually when a series of hydrogen atoms, they get combined with bundles of energy that are obviously electrons. So if I take 4 hydrogen atoms and combine it with your 4 electrons, which are purely energy bundles, then what we get is one helium atom, and which is obviously the fundamental constituent of a star. So we will be talking about star as well later on. So here we can see that the formation of one helium atom is going on due to the combination of 4 hydrogen atoms, which is combined with 4 electrons. But here if I compare the mass of 4 hydrogen atom and one helium atom, then you can see that the mass of the hydrogen atom is greater than that of the helium atom. So where is the rest of the mass has gone? So it's nothing but, again, as Albert Einstein taught us, that again matter can be released in form of energy, simply if I follow the equation of E is equal to mc square. So this is, you can say, the first formed helium atoms that were present in the universe. And as I mentioned, that helium constitute the fundamental unit of stars. So these helium atoms, they started to form multiple stars. How many? It is very hard to quantify how many, maybe billions, maybe hundreds of billions of stars they started to form. And they also under the action of gravity, like again Sir Isaac Newton taught us, that the stars, they also tried to get attracted towards one another under the action of gravity. And during this process, they also started to rotate along its axis, as well as they also started to rotate in a disk kind of a manner, because you can see that if I rotate some particles in a very high speed or high velocity, then obviously that bundle of particles will finally form a disk kind of a structure. So here we can see the formation of the galaxies, where your stars and other particles, including the cosmic dust. We will be talking about cosmic dust in the latter half of the lecture as well. So this cosmic dust, your stars, they are rotating and they are forming a disk like structure, which is represented as a galaxy. Now if I look at our own Milky Way galaxy, then we can see there is a star, obviously not exactly at the edge of the galaxy, but quite far from the center of the galaxy is where we actually stand. So this is our own sun, which is situated at quite a far distance from the center of the Milky Way galaxy, and that is the only reason due to which we can see in a night sky, or if you have a clear sky at, during night time, then you can also see sometimes the Milky Way galaxy. You simply have a view. So as we are sitting quite at the edge of the Milky Way galaxy, we can also see the nearest galaxy, that is Andromeda, which is around 2.5 million light years away. But simply assume that if you were at the center of the Milky Way galaxy, then the rest of the stars and the cosmic dust would have hindered your vision, as well as the vision of the different telescopes and investigators, to find out any other galaxy around our own. So there are several galaxies that are surrounding our own galaxy, and there could be, again talking in terms of numbers, we don't know yet that how many galaxies are present in the universe. Again talking about numbers, it could be billions, it could be hundreds of billions of galaxies that are present in the universe. Now each and every of these galaxies, they are actually moving away from each other based on the idea of the Big Bang. Again they are getting separated from one another at a very fast rate, as well as what is important, there is a consideration of critical mass. Now the question is, what is critical mass? There is not a very clear definition of critical mass, but if I want to understand what critical mass is, that means if the mass exceeds that limit, then something bad might happen, or something, it's kind of a threshold limit of the total mass of the universe, that if it gets beyond that, then there is a chance there will be some inequilibrium. So the critical mass possesses an equilibrium within the universe. So there are a series of you can say there are three options broadly, that what will happen if the critical mass is equal to the known mass plus the dark matter, and whether it could be less than the known mass and dark matter, as well as whether it could be more than the known mass and the dark matter. So dark matter are again nothing but these are small particles or cosmic particles or dust, which have, you can say, nearly very less mass or no mass, and which don't have their own energy in it. So that's why they don't emit any light on their own. So and they are very hard to find as well. So that's what dark matter is. So if I now see at the options, the first one is, if the known mass of the universe plus the dark matter equals the critical mass, then what we get is a flat kind of a universe. So in case of a flat universe, there will be not much change in, or there will be not much expansion, or neither there will be any crunch in the overall dimension of the universe. Then the second, and what we know is presently occurring, or we think at least that presently the known mass of the universe plus the dark matter is less than the critical mass. So that will result into the expansion of the universe forever, and that will lead into the formation of an open universe, that the universe will continue to grow and grow and grow. The third option, and that is again the most important one, that if the known mass plus the dark matter is greater than that of the critical mass, then what will happen, that the universe will expand first, but eventually gravity will take over, and then your stars will try to collapse on one another, your galaxies will start to collapse on one another. So finally the universe will collapse on itself, and this we also refer to as the big crunch. Like we have seen the Big Bang, so this is nothing but the big crunch. So your Big Bang means your universe is expanding continuously, your big crunch means the universe is actually getting shortened and it is getting crunched too. And finally what will be the fate of that crunch? The final fate will be again that the universe will come back to the original singularity or the primeval atoms from where the initial Big Bang started as well. And physicists have suggested that this is like a cycle. So this the period of expansion and crunching will be actually, this is a particular cycle. So this thing will repeat itself again and again. That means there will be a repetition of expansion again followed by crunching, again expansion followed by crunching. So there is a expansion and crash cycle, as we know about the processes that are going on in the universe. Now let's talk about the birth of the stars. As we have seen that if there is a combination of 4 hydrogen atoms, what will you will get is the formation of one helium, and obviously the rest of the mass or the rest of the excess mass, because again to mention the mass of 4 hydrogen atom is more than that of one single helium atom. So the excess mass will be again released as your energy. So that's how your initial star will form from the helium atom. And now if I look at the classification of stars, then generally we classify things in reference to a standard. So here the standard of classification is nothing but our own sun. So our sun's mass is the benchmark for any kind of stellar classification, and one solar mass is equivalent to approximately 1.989 into 10 to the power 30 kilograms. So based on this standard of solar mass, what we have got here, that there are different kinds of stars. If I look at this simple graph, that HR diagram, then you can see that if the luminosity of sun again is considered as a standard, and that is taken as 1. So the luminosity of your white dwarfs are always less than that of 1, but the main sequence stars, like our sun is also a main sequence star, most of the stars in the main sequence will finally go above the luminosity of the sun, and also the temperature will go much higher in comparison to our own star or our own sun. And also there are giants and supergiants that are present, and for that the luminosity is at very high degree. You can say the luminosity of a supergiant is more than 10,000. So you can also think in a manner that if the luminosity of sun is 1, we are talking about a luminosity of 10,000, which is much higher than our own sun. But there is also a very simple classification in the perspective of a geologist again, that stars can be also classified on the basis of its weight in comparison to our own sun, again the solar mass. So you have flyweight stars which have a solar mass of less than 0.5. Remember, our own sun has a solar mass of 1. Then you have the lightweight stars where the solar mass is less than 4 but greater than generally 0.5. Then you have your middleweight stars which have a solar mass between 4 and 8, and you also have the heavyweight star which are more than 8 of our own solar mass. So you can see our sun falls into this category of lightweight star. Now, here I would also like to pose one question, that whether your heavyweight stars will live a longer life, or flyweight stars, which are the tiniest stars, you can say, will have a longer life. So, generally people used to pick up an option that the heavyweight stars will, obviously they are much bigger in size, they have a huge solar mass, so the life of a heavyweight star is much longer. But that is not the reality. The reality is, as you are dealing with a heavyweight star, so that means you are dealing with more number of hydrogen atoms that are getting converted into more number of helium atoms, and the energy released by them is enormous. So as big as the weight of the star, or if a star belongs to the middleweight category or the heavyweight category, it will convert the hydrogen to helium at a much faster rate than a flyweight star, which is having very less amount of hydrogen atoms that are getting converted to the helium atoms. So it's nothing, it's a function of masses. So you can see there is a small table where you can see that if the mass of a star is around 60, then the time span or the total life of that star will be around 3 million years only. But if it's a very flyweight star, like for example 0.1 of the solar mass, then it might live a time of thousands of billions of years. So you can see that it is quite means it's just the reverse what we used to think at an earlier stage of the development of the subject of astronomy as well. So again, to mention here, the larger the star will be, the less time it will live in this universe. The smaller the star will be, the longer and longer time it will stay in our neighborhood. Okay, so coming into, after the classification of star, we look at the obviously the life cycle of a star. And here is an interesting thing, that if I simply look at a main sequence star which has hydrogen burning core, and eventually this hydrogen will get converted into helium in its core, and here the rest of the energy that will be released will obviously converted into heat, and it will be in a very molten kind of a state, you can say, with a temperature of more than 30,000 degrees centigrade or even more than that. So during that, what will happen, that as soon as your hydrogen atoms are getting converted into the helium atoms, what will happen, that some core will start to develop. The core that will be represented by the helium atom, and eventually what will happen, that your helium core will now act as a fuel also to generate other elements in the universe, like we can get the generation of carbon and oxygen out of that helium. So here I would like to mention again that we are all, be it you or me, we are all made up of the carbon that was actually released from the or the conversion of the helium atom that was formed at the core of a red giant at some point of time, and later on it subsequently got modified into several elements. It also got modified into your iron as well, which has a atomic mass of 26, that is the heaviest one in the periodic table, you can see. Also the presence of oxygen, as we know that oxygen are people generally think that oxygen is being derived from the effect of photosynthesis, but it is not like that. Oxygen only gets released during the process of photosynthesis, during the preparation or during the formation of sugar by a combination of carbon dioxide, water, chlorophyll, and obviously under the energy, that is sunlight. So it is only releasing. So green plants only release oxygen, they don't create the oxygen. So actually, be it your carbon, be it your oxygen, these are actually got created during the final phase of conversion of the helium atom to your different elements during the formation or finally the death of a star. So, if I look at the earlier combination of nebula, then a nebula can generate a main sequence star, and from that you can also have two variety of star. One will be the group of supergiant, the other one will be the group of red giant. So, the fate of a supergiant will be finally the expulsion of the energy, the matter that gets converted into the energy, and finally what is left after the release of a supernova, and that is the supernova, and that energy as well as the helium atoms that are getting converted into several elements. So, all your carbon, oxygen, iron, whatever elements starting from the first one to the 92nd one, that is uranium, are all result actually of that supernova which created each and every elements in our universe. And also after the release of this energy, what is left is a neutron star, and obviously it's a relatively colder version of a supergiant. Sometimes what happens that the core also collapses within itself, because your bundles of energy that are electrons get bombarded on the protons, and that finally forms a neutron star, and that also leads to the formation of black hole. On the other hand, if the main sequence star is getting converted into a red giant, it might get modified into a white dwarf, and finally the star cools and reddens, and finally it becomes a black dwarf. So, as I was mentioning that the supernova is the main influencing process which has resulted into the formation of all 92 natural elements in the periodic table. The rest of the elements that are present in the periodic table are being created artificially. So all the 92 natural elements, they are actually nothing but the result of the initial supernova from the star. So, apart from this, we also have cosmic dust that are tiny particles that are made up of various materials like silicates, carbonaceous particles, ices and metals are present in the universe, and also it originates from the stellar explosion. So, also the cosmic dust that we can see or that are present in different galaxies or within the universe, they are also a result of the supernova. So, we will be talking about cosmic dust in larger detail in our next lecture. So, before I finish, there is a quote from Albert Einstein that the most incomprehensible thing about the universe is that it is comprehensible. So, I would like to end my first lecture with this quote from Albert Einstein. Thank you.